Okay, so we're going to look at another example of hydrostatic force acting on a plate. In this case, there's a couple of interesting differences between the triangular plate example that we did in the last video and this one here. First of all, clearly the shape is different. We're looking at a semicircular plate, but then you may also notice that we're using metric units. So I'm measuring the dimensions of things here using meters instead of feet. And then also, kind of interestingly, is that the plate is only partially submerged. It's not completely under the water. Part of it's sticking out. So we're going to take all of that into consideration and see what the problem looks like in this case. So as we did in the previous example, the first thing we're going to want to do is impose a coordinate system on this diagram here. And I think I mentioned this in the previous video as well. There's not a universally correct choice for your coordinate system, but there are some choices that could be easier than others to work with. So for us, the coordinate system is going to look really much or very much the same as the example that we saw previously, where I'm going to let the bottom of this plate be 0. Now let me actually draw the water in here too. So I'm going to have the water line, the water line be like right there. My coordinate system is going to increase as we go up. So the relevant values I want to label here is really just this one, 4. Okay, so from here to here we have a depth of 4 meters. Thinking about this in logical terms, because I have this extra 2 meters, and you should figure out how I know that this is 2 meters here. I have an extra 2 meters of my semicircle poking up out of the water right here. I don't need to worry about what's happening there because that's not submerged. There wouldn't be any hydrostatic force acting on the part of the plate that's above the water. We only care about what's happening between 0 and 4 here. Okay, so we're going to approach this problem, like I said, kind of in the same way that we did in the previous example, where looking at the part of the plate that's under the water, we want to select a rectangle, a horizontal thin rectangle, which corresponds to a subinterval where we would have divided the interval 0, 4 up into a whole bunch of these subintervals. But we're just going to look at one of them. And we're going to say that this edge to this edge is determined by this value xi star. We're imagining that as coming from the ith subinterval. The goal first, as we did in the last example, is to find the area of this rectangle. Now, consistent with our last example, the width is going to be delta x because that is also the width of the subinterval that we're using to come up with this rectangle in the first place. Excuse me. The harder part is finding the length of this rectangle, the horizontal length. So to do that, I'm going to redraw this one more time, where I have my semicircle, which I can never draw super well, but that's going to work. And I'm going to imagine this dashed line here as this line right here, this solid line. So I'm just going to look at that line in the middle, because the length of that line would be the length of this rectangle. Now what I want to do is think about how to come up with the length of this. And what I'm going to do is go to the center of my semicircle, which is like right here. And I'm going to draw a radius that goes out and meets this line segment right here, and then a perpendicular line right here. Okay, now the next question is, do I know the lengths of any of the sides of this right triangle that I just created? I actually know 2 of them. One of them is xi star, because that would represent the height from 0 from here to that dashed line. So xi star represents that leg of my right triangle. I don't know this leg, so I'm going to call it A, but I can see that whatever it is, it's half of the length that I'm looking for. So if I can find A, I'm going to double it to get the length of that line, which is the length of that rectangle. This hypotenuse right here, I can say is 6. And the reason I know that is because it's also a radius of this semicircle. And we know from up here, this semicircle has a diameter of 12 meters. So half of that is the radius. That's where I'm getting 6 from. I can solve for A using the Pythagorean theorem, which would be the square root of my hypotenuse squared minus this leg squared. So square root of 36 minus xi star squared. That's from the Pythagorean theorem. Okay, so that means that the length of my rectangle, which is up here, but here's the length of it represented as a line, is double this. That means that the area of that rectangle is equal to 2 times the square root of 36 minus xi star times the width of the rectangle, which again is delta x. Okay? So now I have the area of my rectangle. The next step, like we saw in the previous example, is to find the hydrostatic pressure acting on that rectangle. So we're going to do that thinking about how this works in metric units. Remember, we want the density of the fluid, which is water in this case. We want the acceleration due to gravity. That's g, or 9.8 meters per second squared. And then we want the depth. So I'm going to call that di, because this is the ith rectangle that we're looking at. The depth below the water. And that's all three of these quantities are something that we can determine just from the problem itself. So let's find some of those pieces here. The density of water in metric units is 1,000, and that's in kilograms per meter squared. Excuse me. I'm sorry, meters cubed. So it's kilograms per cubic meter is the density of water. And then G is acceleration due to gravity, which we've used many times in the past. We know that that's 9.8 meters per second squared. What is the distance? What is di? Well, remember, the distance represents the depth below the water that we're finding our rectangle. So basically, how far below the surface of the water until I get to that dashed line right there. And I can see that that would be 4 minus xi star. So that's where I'm going to get this, 4 minus xi star, like that. Okay. Excuse me. Sorry, I've got something going on with my throat right now, so pardon all the noise. All right, so this is great. Now what did we need next? We needed force, Fi, which as before is the same thing as Pi times AI. It's pressure times area. That's how we find force. So I'm just multiplying these two results together. Let's do a little bit of simplifying here. So I can see that if I were to multiply this guy times this guy, I have some constants that can all be multiplied together. 1,000 times 9.8 is 9,800. And then if I multiply that to this 2 right here, I'm going to get 19,600. Okay, so I'm doing a little bit of cleanup there. And then I have this 4 minus xi star. And then I have this radical as well, 36 minus xi star squared. And I think I forgot to put the second power up there, so let's include that. Then I have a delta x. Okay, so as we saw in the previous example, this will end up turning into my integrand, because when I want to make my approximating rectangles that I'm adding up precise, I take the limit as n goes to infinity. It turns the things into a definite integral, so that my force is the definite integral from 0 to 4. We know that it's from 0 to 4 because, as we said before, these rectangles will only occupy the part of my semicircular plate here that exist, or that are under the water, which only goes from 0 to 4. 0 to 4 of 19,600. I'm going to have 4 minus x, just x. It's not going to be xi star anymore because we've applied a limit, times the square root of 36 minus x squared, and then my delta x becomes a dx. I'm going to write this in a slightly different form. First of all, I know I can pull the 19,600 out, and then I can distribute this radical into this set of parentheses here, and I can split it up into two integrals. So this will look like the integral from 0 to 4 of 4 times the square root of 36 minus x squared dx minus the integral from 0 to 4 of x times the square root of 36 minus x squared dx. I'm doing this because each of these integrals has to be evaluated using a different technique. So this integral right here, I'm going to leave that there for a second. This integral right here, the integral from 0 to 4 of, let's take the 4 out, and I have the square root of 36 minus x squared dx. To evaluate this, I'm going to use a trig sub because it's exactly in that form that we use those trigonometric substitutions for. The form of this suggests that I should let x equal 6 sine of theta, which means dx is equal to 6 cosine of theta d theta. So now what do we have here? 4 times the integral from 0 to 4 of the square root of 36 minus, so this is going to be 6 sine theta all squared, which gives me 36 sine squared of theta. My dx here is going to become 6 cosine of that, theta d theta. And then I'm going to do a whole lot of simplifying here. So let's see. I know I can factor a 36 out, which after taking the square root is going to become a 6 out here. Here's another 6, so those will multiply together to make 36. And then I can pull that out and multiply it to this 4 out here. 36 times 4 is 144. Okay, now what's left when I do that? Well, first of all, and actually I just realized I forgot to do something really important here. I made a trig substitution, but I forgot to change my limits of integration. So let me back this up a step. Let's figure out what those limits of integration should be. I should have set 0 equal to the x value in my substitution. 0 equals 6 sine of theta. This could only be the case if sine of theta equals 0, which we know means theta equals 0. So it's okay for me to leave that 0 where it is. But now we need to put a 4 there as well. 4 is equal to 6 sine of theta, which means that sine of theta is equal to 4 over 6 when I divide by 6, or 2/3. That's a value that I don't recognize from my unit circle. So to solve for theta, I just need to put an inverse sine of 2/3 there. So this is actually the inverse sine of 2/3. Okay, now we're caught up. So these are my limits of integration. Recall what we did here. We factored the 36 out. So really what's left in here is a 1 minus sine squared, which we know the whole point of this was to make a cosine squared out of that. That lets me take a square root and get just cosine. If I take the cosine that I get from this step and multiply it to that cosine there, I'm going to have cosine squared of theta d theta. So that's good. We needed that. That cosine squared, we've dealt with trigonometric integrals already. We know that the approach to that we need to handle this is to use a power reduction formula. So remember, cosine squared is equal to 1/2 times, and then in parentheses, 1 plus cosine of 2 theta. The 1/2 that appears from that identity, I can bring that out and multiply it to that 144 right there, which gives me 72. Okay. Now what's left here is 1 plus cosine of 2 theta d theta. Okay. Now the integration is a lot more straightforward. If I integrate, I'm going to get theta here plus 1/2 sine of 2 theta from this step here. That's a straightforward u substitution that would do that. We're going from 0 to the inverse sine of 2/3. Let's go a little bit further. So I can see that I have a sine of 2 theta here. And I think a way I would like to approach that is use a double angle formula for the sine function. Now I know that the sine of 2 theta that's in there can be converted to 2 sine of theta cosine of theta. But the 2 that would appear at the front of that is going to multiply with this 1/2 and cancel it out. So really, this just simplifies down to sine of theta cosine of theta. From 0 to the inverse sine of 2/3. Okay, now I did say in the previous video that I'm going to start skipping the work going from this step to an answer. I'm not going to do that this time though, because I've got this inverse sine thing in here, and those are potentially a little trickier to work with. So let's just figure out what this would be. First of all, I see that if I plug that 0 as my lower limit into this, I'm going to get a 0 here and a 0 here, because sine of 0 is 0. So the only part of this that matters is the inverse sine of 2/3. If I plug that in, I'm going to get the inverse sine of 2/3 there. And then I'm going to get, so let's think about what would happen if I plug this in. Plus sine of the inverse sine of 2/3. The sine and the inverse sine cancel each other out when I plug one into the other, so I'm just going to be left with a 2/3 there. But what about this guy right here? Cosine of the inverse sine of 2/3. Let's think about what that looks like for a second. If I have the cosine of the inverse sine of 2/3, we've seen from our trig sub section that if you think of this theta right here as the inverse sine of 2/3, then that means sine of theta equals 2/3. So that's opposite over adjacent. That kind of gives me a couple labels that I can use on that right triangle. Then if I do the Pythagorean theorem to solve for that third missing side, that's 9 minus 4, which is 5. I take a square root, and I get root 5 there. Cosine of theta would be adjacent over hypotenuse, or root 5 over 3. That's what happens here. When I have this cosine of theta and I plug this inverse sine of 2/3 into it, I get this, which comes out to just the square root of 5 over 3. And that's what this is going to evaluate to. I can go further than that, but right now I'm going to leave it alone because it's only one of 2 integrals that I needed to solve. What I am going to do is I'm going to just give it a name. I'm going to call that A, because in a final step, I'm going to substitute that A in for something later. But that's just to give it a label so that we can come back to it. Okay? I'm going to go like this to kind of separate the work out a little bit. Coming all the way back up here, all of this work was to solve this first integral, but there's a second one right there. And that one is not very difficult to solve by comparison, because we can do that one with a pretty straightforward u substitution. We don't need a trigonometric substitution. It's really just the fact that this x is here that makes that possible. Here I can set u equal to 36 minus x squared, so that du is negative 2x dx. And then I can simplify or cancel that negative 2 out by multiplying both sides by negative 1/2. Okay, so that simplifies things a great deal. First of all, when I do the u substitution, if I plug a 0 in here, 36 minus 0 is 0. So my lower limit of integration is 36. My upper limit of integration, if I plug a 4 in, 36 minus 4 squared is 36 minus 16, or 20. Okay, this negative 1/2 from my u substitution can come out right there. And then what's left? I have the square root of u, and then I have what's equal to negative 1/2 du. So all of this becomes u to the 1/2 power du. That's an easy integral to do compared to what we've been looking at. Let me use the negative to flip the signs here so that I get a positive 1/2. And then when I take my integral, I'm going to get 2/3 times u to the 3/2. So times 2/3 u to the 3 halves. And because I used my negative here to flip the sign here, I'm going to get 36 and 20. Okay? Notice that the 1/2 and the 2/3 cancel partially, and I get a 1/3 out of that. So I'm going to end up with 1/3. Then when I plug 36 into here, the square root of 36 is 6. If I cube that, I get 216. When I plug a 20 in there, that doesn't simplify as nicely, so I'm going to leave that in the form 20 to the 3 halves power. Let's call this one B. Okay, so now I have A and I have B. Coming all the way back up here, where we first were trying to evaluate our force, I see where A appears right there, and I see where B appears right there. So really, to compute my force, what I want to do is 19,600 times, in parentheses, A minus B. Okay? So finally, our force is equal to 19,600 times A minus B. Now, what I would do at this point, I would take a calculator and I would compute A, because all of this can now go into a calculator. Same thing with B. Plug all of that in, get something in my calculator, and then take those results, put them over here. Again, use a calculator to work this stuff out. And I'm going to finally end up with an answer of about 904,181.68. And these are newtons. Remember, we started in metric units. So our units of force here would be newtons. Okay? As you can see, there is a lot to do in a problem like this. And that's, the setup is the first step, but then we ended up with integrals that required some integration techniques, some kind of creativity to solve. So that's all I'm going to do in this video. Starting in the next video for 8.3, we're going to shift our focus to the other application that we're looking at in this section.